Hello, this is John Miyares, and now that we've had a chance to explore the trigonometry as it applies to right triangles, we're going to be looking now at how we might solve non-right triangles. There's two sections to be covered here, and they cover two main ideas that are intertwined but take different approaches. The first thing we'll do is talk about finding the area of a triangle, and then we're going to talk about solving triangles that are not right triangles. Now, in a recent ORT session, we explored this idea of what happens with sines and cosines of obtuse angles and how those values relate to their supplements. And when I say the word supplement, I'm talking about supplementary angles. Two angles are supplementary if their measures add up to 180 degrees. We had these tables and filled them in using our calculators. And if you weren't in attendance at the live session when we did this, I'd advise pausing this video for a couple minutes and using your calculators to fill in these values that you see here so that you'll be ready to discuss the patterns. This is going to be an important aspect of our study for the rest of this section. So here's what they look like all filled in. Please take your time to look at these numbers for a minute, and we're going to discuss some patterns in them in just a minute. Now, what I'm hoping you saw were the following relationships. First, making sure that we have our vocabulary straight. We're going to define complementary angles as two angles whose measures add up to 90 degrees. As you look at the first table, what I'm hoping you saw is that the sine of any acute angle would equal the cosine of its complement, and vice versa, the cosine of any acute angle will equal the sine of its complement. This means that you're going to see the sine of 30 degrees equals the cosine of 60, or that the sine of 40 equals the cosine of 50, and so on. This idea we already did discuss in section 6.2. Now, two angles that are supplementary are angles whose measures add up to 180 degrees. And when we started looking at obtuse triangles, what I'm hoping we saw is that the sine of an obtuse angle will equal the sine of its supplement. So the sine of 120 degrees will equal the sine of 60, or the sine of 140 degrees will equal the sine of 40 degrees. This is going to have a few ramifications moving forward with our study of non-right triangles, but the most important aspect of this is that the sine function is no longer a one-to-one function once we go beyond angles that are acute. For cosine, what we see is that the cosine of an obtuse angle will be the opposite of the cosine of its supplement. So we're just changing the sign from positive to negative. What this tells me is if I have a geometry problem where the cosine comes out negative, that means I'm going to be working with an obtuse angle, versus when the cosine of an angle is positive, I'm going to know that the angle has to be acute. So at least with cosine, there's still some one-to-oneness within our triangles that will help us for the moment. But I'll warn you that it's not going to last for long. For tangent, what we see is that the tangent of the obtuse angle will be the opposite of the tangent of the supplement. For the most part, with these larger angles, we're just going to focus on sine and cosine and not worry too much about tangent for now. Now, let's switch gears for a few minutes and talk about how to compute the area of a triangle. One way they introduce in these sections to find the area of a triangle is this convoluted formula known as Heron's formula, or sometimes known as Hero's formula. Given the values of the lengths of the three sides of a triangle, A, B, and C, the area of a triangle can be calculated as the square root of the quantity S times S minus A times S minus B times S minus C, where S equals 1/2 of the quantity A plus B plus C, or sometimes we call that the semi-perimeter of the triangle because it is half the perimeter of the triangle, perimeter being the sum of the sides, lengths of the three sides in the triangle. Now, you're probably wondering why we would want to have a formula like this when we have a perfectly decent formula for the area of a triangle, which just involves taking half the base times the height. Well, in this case, we might not be given the height of the triangle. We might only be given the lengths of the sides of the triangle. So this gives us an alternate approach to finding the area of the triangle without first having to find the height, which sometimes in situations like this can be very difficult. This might make more sense if we look at some examples. So let's try this. Suppose you're asked to find the area of a triangle where the three side lengths given are 6, 8, and 10. Here's a picture of a triangle that describes that situation. Now, the good thing about this particular example is that it is a right triangle, which can be easily verified using the 1/2 base times height formula for the area. But let's try working through Heron's formula to see what happens. The formula says that the area will be the square root of s times s minus a times s minus b times s minus c, where s is the semi-perimeter of the triangle. So S will be half the sum of the lengths of the three sides, 6 plus 8 plus 10. So you have half of 24, which will be 12. S equals 12. We'll now use this value of S in our computation for the area formula, substituting in S equals 12, A equals 6, B equals 8, and C equals 10 into this formula. We can get this to simplify as the square root of the product 12 times 6 times 4 times 2, which simplifies as the square root of 576, or 24. Now, notice if you wanted to find the area of this triangle using the 1/2 base times height formula, we can still do that knowing that what we have here is a right triangle. We can use 6 as the base and 8 as the height. 6 times 8 is 48, half of that is 24. So you see, we can get the same answer. Here's another example. Find the area of a triangle where A equals 5, B equals 6, and C equals 7. A quick sketch this time will easily show you that this is not going to be a right triangle. You can also run the numbers through the Pythagorean theorem too, and you'll see that 5 squared plus 6 squared does not equal 7 squared. So using the 1/2 base times height formula is not going to be an easy option here for finding the area of a triangle. So let's try this with Heron's formula. The semi-perimeter, half the sum of the sides, it will be half of 18, which comes out to be 9. Plugging that into the formula, we have the square root of the product s, which is 9, times 9 minus 5, which is 4, 9 minus 6, which is 3, and 9 minus 7, which is 2. Multiplying that out under the radical is going to give you the square root of 216, which simplifies as 6 square roots of 6, or decimalizes as 14.7. Let's look at a different area formula, which I do have more use for than Heron's formula. Here, given the values of the lengths of the two sides of a triangle A and B, and the measure of the included angle C, the measure of the area of the triangle can be calculated as 1/2 times A times B times the sine of angle C. Now, you might be thinking this is more complicated than the first one that we worked with. However, we can actually prove that this one is legit and maybe get a better feel for it in the process. Suppose we start with our own known formula for the area of a triangle is 1/2 base times the height, which in this labeled triangle simplifies as 1/2 of B times H. Now, with respect to angle C, we could look at the height h as the opposite side of the right triangle formed where the height creates the right angle. and side A is the hypotenuse of that little right triangle. Using what we learned in section 6.2, this makes the sine of angle C equal to h over A, the opposite over the hypotenuse. Cross multiplying, you get h equals A times the sine of C, which we can then substitute for h into that other area formula to get the area equals 1/2 of B times A sine angle C. Rearranging the terms using commutativity and putting the expression in alphabetical order gives you 1/2 A times B times the sine of angle C, which is the formula in the red box. Let's try an example of this. For the area of a triangle where side A has length 15, side B has length 10, and angle C has a measure of 30 degrees. What I'll say here is that this triangle is not drawn to scale, but we can still use it for our purposes. Our formula is given as area equals 1/2 AB sine angle C. So we can just substitute those values into the expression as we see them. Simplifying things, 10 times 15 will be 150. The sine of 30 degrees is 0.5. And multiplying all that together will give you an area of 37.5 for this triangle. Let me give you one to try on your own. Find the area of a triangle where A equals 8, B equals 12, and angle C measures 60 degrees. Try this one on your own, and in the meanwhile, you should pause the video until you get through it. So again, we're just going to substitute our givens into this formula, which is going to give us 1/2 of 96, which is the 8 times 12, times 0.866, the sine of 60 degrees, which will give us an area of approximately 41.57. Now, you might be looking at this and saying that this formula seems somewhat limiting because it requires you to have sides A and B as well as angle C. However, this formula can be generalized for when you're given any two sides of the triangle and the angle in between. Here's a diagram showing that situation here. Remember that depending upon which way you rotate the triangle, it has three different height measurements. We call these segments altitudes, and depending upon which way we rotate it, any one of them could be used to measure as the height of the triangle. In previous examples, we used the segment that was labeled in the diagram here, going from B to H3 as our height, and then used that comparing angle C. Our opposite side was this altitude marked with a little h3, and the hypotenuse was A, giving you the sine of angle C. However, there's nothing to say that they couldn't measure the height as the length of the altitude coming off of point A and coming across here and saying that the not only could we have the area of the triangle be 1/2 A times B times the sine of angle C, but we could have it as 1/2 B times C times the sine of angle A. Or flipping around and looking at this third altitude, we could say it's 1/2 A times C times the sine of angle B. All of these values should be equal to each other because we're talking about calculating an area for the same triangle, but just in three different ways. The one consistent thing we have between all three of these approaches is that the two sides that we know form the angle that is also known. Or you can say that the angle that is given between the two given sides. Angle C is formed by sides A and B. Angle A is formed by sides B and C, and angle B is formed by sides A and C. Now, here's where the magic begins. One thing that someone discovered is that if you divide everything here by 1/2 A, B, and C, what you're going to see happen in the first case, the A and the b and the 1/2 are going to cancel, leave you with sine of c over c. In the second expression, the 1/2, the b, and the c are going to cancel, leaving you with sine of a over a. And in the third term, the 1/2, the a, and the c cancel out to give you the sine of angle b over little b. This three-sided equation here is something known as the law of sines. So some of you are thinking to yourselves, yeah, so what? Well, what this conclusion basically provides for us is a strategy for finding the missing sides and angles in non-right triangles. It's based on the idea that the ratio of the sine of any angle to the length of the side opposite that angle will be proportional to the ratio of the sine of any other angle in the triangle to the length of its opposite side. Specifically, in any standard triangle labeled ABC, the sine of angle A over side A will equal the sine of angle B over side B and the sine of angle C over side C. Now, your textbook and some other textbooks actually show these same proportions but upside down, as I've shown here. Side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. The process is the same. I just happen to learn it this way instead of that way. So you're more often going to see me write it using it as the sine of the angle over the side across from it rather than putting the side over the sine of the angle. The second approach will give you the same answers. Now, this law will not work for every situation. It works best when you are given two angles already and one of the sides of the triangle, or two sides and the angle that is not between those two sides. Let me try drawing a picture of this to kind of show you what we're talking about here. So, one way of looking at this, when I say AAS, what I'm really mean is I want two angles and a side that's not in between. So I could say I've got angle A, I've got angle B, and then maybe the third side over here, that side not being between the two. Now, the reality is that if you're given the two angles, you can always subtract from 180 to get this third angle over here. And if you're given one of the sides, then you're just solving a couple of separate proportion problems in order to find the missing two sides. Now, let me erase what we have here for a second. When I say SSA, I'm talking about getting two sides and the angle not in between the two. So let's say what I have here is this side over here, side C, and then maybe I'll have side A is given over here, and then I'll have angle A, where angle A is not the one that is between the two sides. That second example is a little bit more complicated. Let's just start with the angle side situation here. Let's try an example where we're given the measures of the two angles and a side. So here we're asked to solve the triangle using the law of sines with the given conditions. It's also asking us to find the area of the triangle. We're given side A equals 15, angle A equals 64, and angle B is 42. Here's a picture of that triangle so you can get an idea of what it is we're trying to look at. Side A is across from angle A, angle B is put at the top. If we wanted to compute angle C, then all we'd have to do is subtract 180 minus 64 minus 42 to get 74 degrees. Now that we have all three angles, let's start solving for the missing sides. To find the length of side B, we're going to set up the proportion sine of angle A, which is 64 degrees, over side A, which is 15, equals the sine of 42 degrees, which is angle B, over side B, which at this point is unknown, but would be the side across from angle B not explicitly marked in this diagram. When solving proportion problems like this, what you'll want to do is cross multiply and set the cross products equal to each other. So you see you have b times the sine of 64 degrees equals 15 times the sine of 42 degrees. Knowing that the sine of 42 degrees and the sine of 64 degrees are decimals that can be computed on the calculator as part of this process, we can leave them as seen here and then just type in the expression just as we see it on the screen. Remember, we do need to be in degree mode, and remember, we need to insert some parentheses in our expression in the calculator in order to make sure we're handling the order of operations correctly. When we do this, you should get side B equals 11.167. For side C, we're going to follow the same procedures. Side C is across from angle C, which we computed as 74 degrees. So again, we're going to set up the proportion sine of 64 over 15 equals sine of 74 over C. We can cross multiply to say c times the sine of 64 equals 15 times the sine of 74, then we can divide both sides by the sine of 64 degrees, which is going to give us a measure of 16.043 as the length of side C. Now that we have everything, we still need to find the area of the triangle. We have our formula A equals 1/2 AB sine angle C. We plug in our givens and the computed values into this formula. Eventually, we're going to get an area of 80.51. Now, one thing I want to notice here in these triangles is the biggest side seems to be across from the biggest angle, and the smallest side is across from the smallest angle, and the middle-sized side is across from the middle-sized angle. That's something we can use as a double check because that's essentially the nature of the law of sines. The bigger the angle, the bigger the side is across from it, and vice versa. The longer the side across from an angle, the bigger the angle is. Here's one I want you to try on your own. You have side A equals 20, angle A equals 125 degrees, and angle C equals 23 degrees. A quick calculation will get you that angle B is the difference from 180 degrees, which will get you 32 degrees. A diagram of this one is also shown. Why don't you pause the video for a few minutes and give this one a try on your own using the law of sines. All right. In our first application of law of sines, we may try to find side C because we're given angle C. So we have this proportion here, sine of 125 over 20 equals sine of 23 over C. We can cross multiply and set our cross products equal to each other. Then we can divide both sides by the sine of 125 degrees to get a length of side C that is approximately 9.54. For side B, we'll take the same approach. We have the sine of 125 over 20 equals a sine of 32 over B. We want to cross multiply, and then we want to divide out the sine of 125. We can punch that into our calculators, and we will get a length of 12.94 for side B. Again, the biggest side length, A equals 20, comes from being across from the biggest angle. The smallest side length, C equals 9.54, is across from the smallest angle. We still need to evaluate the area, so we'll plug in what we can into the formulas that we're given, which will give us an area of, eventually, 68.57. Now, we could have picked any of the three variations of that area formula, or we could have used Heron's formula to find the area, and we should get the same answer either way. Heron's formula is probably going to be ugliest to use because the two side lengths B and C are both irrational. So using the formula that we picked here, A equals 1/2 A times B times the sine of angle C is going to probably be best because you only have one computed value that you're working with, and that's going to be side B. All of the other values are known and happen to be pretty clean. Now, the other set of triangles that can be solved for using the law of sines are those where you have two sides and the angle not between the two. However, the process does not always come up with a unique solution, mostly because, unlike with triangles where you're given two angles and a side in between, or two sides and the angle in between are all three sides, there is no guarantee that given two sides and the angle not between them will give you a triangle at all, much less a unique one. This is because when you're given two sides and one angle, the first thing you want to try to do is solve for the second angle. And if you have something that comes up with, say, sine of theta equals zero point 0.5, we saw before in our earlier slides that there are two possible solutions to this, one acute and one obtuse, that can satisfy this condition. This means that under some circumstances, we can be given two sides and the angle not in between and end up with two triangles that satisfy those conditions. Here is such an example. We have side A is 6, side B is 8, and angle A is 45 degrees. This seems innocent enough until you realize that this second triangle here meets the same conditions. Angle A is 45 degrees, side A is 6, and side B equals 8. What happens is that when we go to solve for angle B, we can get two different solutions that both happen to work. We'll look at this example more closely on the next slide. What can also happen is that the two sides and the angle not in between, it's possible to get a situation where the third side that is provided is too short to connect to the triangle, and consequently, it's just sort of floating out there, and we don't even really have a triangle. We're going to look at this example more closely as well. Let's see if we can make sense of this dilemma by exploring this example presented on the previous slide. We're asked to solve the triangles using the law of sines given that side A has length 6, side B has length 8, and angle A measures 45 degrees. The first thing we'll need to do is apply the law of sines by saying that the sine of angle A over side A equals the sine of angle B over side B. With our givens, that's going to look like what you see here. Sine of 45 degrees over 6 equals the sine of angle B over 8. Cross multiplying, we're going to get 6 times the sine of angle B equals 8 times the sine of 45 degrees. Dividing by 6 gives us the sine of B equals 8 times the sine of 45 over 6, which if we punch that into the calculator, will get us the sine of angle B equals 0.9428. Now from here, we could punch that into the calculator, but the calculator will only give us the acute solution, not the obtuse solution. The acute solution is 70.53 degrees. However, we need to recognize that angle B could possibly also be obtuse and have the same sine value. So we'll look for its supplement to get angle B also, and that would be 109.47 degrees. Now you're probably asking yourself, if I've got this $100 calculator that's supposed to be the greatest thing since the slide rule, why can't it give me both answers to this problem right away? Well, it has to do with the fact of how the inverse sine is defined as a function. I don't want to get into it too much now, but the short answer as to why the calculator won't give you both the acute solution, 70.53 degrees, and the obtuse solution, 109.47 degrees, is the same reason why the calculator, when asked to find the square root of 4, gives you only the number 2 and not the number -2. In functions, remember, in a function, for each x, there can only be one y. And the inverse sine function is a function. So if we ask the calculator to give us the inverse sine of something, it's only going to give us one answer. And by default, it will give us the acute solution. Anyway, that's a long winded explanation for this, but let's now talk about what that means. Coming back to our problem, angle B could either be 70.5 degrees or 109.5 degrees. What we're going to do from here now is assume at a minimum that the acute solution is valid and try to solve the triangle from there. So if we assume that angle B is 70.53 degrees, we can solve for angle C knowing that the sum of the three angles always adds up to 180. To get angle C, we'll subtract and get 64.47 degrees. From there, we'll use the law of sines to find side C, starting with angle A and side A for comparison purposes, because those were our givens. And as mentioned before, it's always best to use our givens rather than any calculated values that are provided. We can cross multiply, and then we can divide just like before, and we're going to end up with side C being approximately 7.657 units long. So here's basically what that triangle is going to look like. And now we have what we call the acute solution, which is given here with the three sides known: A equals 6, B equals 8, C was calculated 7.657. Our three angles we were given: angle A is 45, angle B we calculated as 70.53, and angle C we subtracted to get 64.47. This is what I call the acute solution to this triangle. Now let's look at what happens if we assume that angle B is obtuse instead of acute. If angle B had a measure of 109.47 degrees, then angle C would measure 25.53 degrees after we subtract 109.47 and 45 from 180. Applying the law of sines here, you're going to get sine of 45 degrees over 6 equals the sine of 25.53 degrees over C. Cross multiplying and then setting the cross products equal to each other gives us this equation here. Then we can divide by the sine of 45 degrees on both sides and punch it into our calculator to get an approximate length for side C of 3.657. So here is what that triangle looks like. If you compare it to the triangle directly above it, you're going to see that angle A is the same, side A is the same, side B is the same. However, since we didn't know what angle B looked like, we have the flexibility to allow for it to be either acute or obtuse and still have something that will satisfy the initial conditions of the problem. So here now is my obtuse solution. You have A equals 6, B equals 8, C equals 3.657 as your three sides. As for your angles, you have angle A is 45 degrees, angle B is 109.47, and angle C is 25.53. Now, this process doesn't always generate two solutions, but it is something we have to consider and check for every time. Here's another example. Suppose we have sides A equals 6, B equals 5, and angle A is 50 degrees. Let's say we start by applying the law of sines to say that the sine of angle A over side A equals the sine of angle B over side B. Just like before, we can cross multiply, and then we'll divide by 6 to get sine of B by itself, 5 times the sine of 50 degrees, all divided by 6, which will give you sine of B equals 0.63837. Next, we'll take the inverse sine of this on our calculator, which will get us the acute solution. Angle B will be equal to 39.67 degrees. But we also need to manually consider the potential obtuse solution. We'll take the we'll take the supplement 180 minus 39.67 equals 140.33 degrees. Just like before, we're going to start by assuming the acute solution is actually possible. So if we assume that angle B equals 39.67 degrees and angle A is 50 degrees, That leaves angle C to equal 90.33 degrees. Applying the law of sines again, we'll say that the sine of angle A over side A equals the sine of angle C over side C. We'll plug in our knowns, then we'll cross multiply, set the cross products equal to each other, and then we'll divide both sides by the sine of 50 degrees, put that in the calculator, and we'll get side C is 7.832. Next, we have to consider the possibility that there's a second answer. If angle B were 140.33 degrees, which was the supplement of 39.67 degrees, then the measure of angle C would be a negative number. Clearly, that does not make sense. So since angle B being obtuse generates a nonsensical answer for angle C, we can assume that there's only one solution to this problem, and I put it in the red box above here. Side A equals 6, side B equals 5, side C equals 7.832. Angle A measures 50, angle B measures 39.67 degrees, angle C measures 90.33 degrees. Now, one other thing we can do is check for reasonableness. One thing we discussed earlier was the idea that the bigger the angle is, the bigger the side is that is across from that angle. In this side, we see that side B is smaller than side A, which means that angle B has to be smaller than angle A. So it's not possible for angle B to be an obtuse angle in this case. In the previous example on the last slide, side B was actually larger than side A, which meant that angle B had to be bigger than angle A. We just didn't necessarily know how much bigger it could be, and that's what opened up the door to really having it be either acute or obtuse. Let's look at one more. And again, this is an example I alluded to earlier. Solve the triangle using the law of sines with the given conditions. Again, here's the law of sines. I want to take the sine of angle A over side A equals the sine of angle B over side B. Cross multiplying here gives 4 times the sine of B equals 7 times the sine of 55. And if we divide by 4, we aren't seeing any problems so far until we turn things into a decimal and get the sine of B equals 1.4335. Here's our dilemma. In section 6.2, we discussed the idea that the values of the sine function only range between 0 and 1 because you're setting up a ratio of the opposite side to the hypotenuse. If the hypotenuse is always supposed to be longer than the opposite side, then the fraction opposite over hypotenuse can never be bigger than 1. So our conclusion is that there is no such triangle that can satisfy these conditions, or in other words, there is no solution to this triangle. If we try to draw this situation out, what you're going to see is that side A is too short to connect to side C at the bottom of the triangle, no matter how much we want to swing that dangling segment out there, either outward or inward. So the moral of the story here is that when you're given two sides and the angle not in between, the SSA situation, two sides and the angle not in between, you might have one solution, you might have two solutions, you might have no solutions, but you won't know until you run it through the system. We will not have this problem if you're given two angles and one side, whether that's a side in between or a side not in between. The other major set of formulas that get introduced in section 6.6 that can be used for solving triangles is called the law of cosines. In some ways, the law of cosines is easier than the law of sines because you're not going to run into the kind of ambiguity that we did with the law of sines. However, the formula looks a lot more complex. It's going to look like this. It says in any standard labeled triangle ABC where we're assuming sides A, B, and C are directly across from angles A, B, and C respectively, then there's a relationship between the side lengths that says that c squared equals a squared plus b squared minus 2 times a times b times the cosine of angle C. Now, this looks intimidating, and it does get worse. It could also be written as a squared equals b squared plus c squared minus 2 times b times c times the cosine of angle A. Or it could be written as b squared equals a squared plus c squared minus 2 times a times the cosine of angle B. Now, you might be worried that you have to now memorize three different formulas, but realistically, you do not. I'd actually focus on the first one, which is very closely resembling of the Pythagorean theorem. You see the c squared equals a squared plus b squared, but then it has this fudge factor that's subtracted out to account for the fact that angle C isn't a right angle this time. In fact, if angle C was a right angle, you might remember from the beginning of this presentation that the cosine of 90 degrees is 0. And you can verify that in your calculator. The cosine of 90 degrees is 0. So if I have a right triangle, that whole last part falls out and degenerates into c squared equals a squared plus b squared. But ultimately, what this is saying is that if you want to find the length of one side and you know the lengths of the other two and the measure of this angle between those two sides, then we can plug them into this formula to get the length of the third side. So this formula is going to work best if you have two sides and the angle in between, but it will also work well if you're given all three sides, side A, B, and C, and plug them into the formula and you'll be able to solve for angle C. Here's an example where you're given two sides and the angle in between. We'll have A equals 15, B equals 10, C equals 60. We want to use the law of cosines to first find the length of side C, and then we'll try to find the measures of the angles and the rest of the triangle. The law of cosines formula we'll start with is going to be the first version, which I said is really the only one that I would suggest you memorize. Plugging in our knowns into the expression, we have 15 squared plus 10 squared minus 2 times 15 times 10 times the cosine of 60 degrees will equal c squared. Expanding and simplifying this expression, you see we have 225 plus 100 minus 2 times 150 times 1 half, which is the cosine of 60 degrees. That's going to reduce to c squared equals 175, which would mean that c is going to be approximately 13.229, or more exactly, the square root of 175, or 5 times the square root of 7. Now that we have side C, we don't have to use the law of cosines to find the other angles. We can, but at this point, the law of sines is probably going to be easier to work with. I'm going to solve for angle B first because I happen to see that side B is smaller than side A, so therefore angle B has to be smaller than angle A, and that's going to force angle B to be acute, since you can't have more than one obtuse angle in a triangle, and if you did, the obtuse angle would certainly not be the smallest one. So we can cross multiply and set the cross products equal to each other. We'll divide by the 13.229 on both sides, and then punch the result in the calculator to get the sine of angle B is 0.65465, which translates into angle B measuring as 40.89 degrees after we take the inverse sine. Again, we don't need to worry about there being an obtuse solution here because angle B has to be smaller than angle A, which means angle B has to be acute. To get angle A, we'll just subtract from the two known angles from 180 degrees, and that's going to give us 79.11 degrees. So here is our final solution to the triangle. Side A was given as 15, side B is given as 10, side C was calculated as 13.229. For our angles, we were given angle C is 60 degrees, angle A was calculated 79.11 degrees, and angle B is calculated as 40.89 degrees. Here's an example where you're given the three side lengths in the triangle and asked to find the measures of the three angles. Again, here's a case where you can start with one formula, substitute our givens, then rearrange the expression to solve for angle C. So we have 8 squared equals 6 squared plus 7 squared minus 2 times 6 times 7 times the cosine of angle C. So you've got 64 equals 36 plus 49 minus 84 times the cosine of angle C. Be careful with the order of operations that you don't try to combine the minus 84 with the 36 and the 49. What we need to do is subtract the 36 and the 49 to the other side. Then we'll end up dividing both sides by negative 84, which gives the cosine of angle C reducing to 1/4. Angle C then will be the inverse cosine of 0.25, which gives us 75.52 degrees. Now we'll use the law of sines to find another angle, knowing that we have angle C. Let's say we try to find angle B this time. We can say that the sine of angle C over the length of side C equals the sine of angle B over length of side B. When we cross multiply, we can set the cross products equal to each other. So you have 8 times the sine of B equals 7 times the sine of 75.52 degrees. We'll then divide both sides by 8 and then punch that into the calculator to reduce becomes 0.8472 equals the sine of angle B. Taking the inverse sine of this gives us angle B equals 57.91 degrees. Again, I don't need to consider the obtuse solution here because we know that side B is shorter than side C, so angle B has to be smaller than angle C. So this measure that we have for angle B, 57.91 degrees, has to be our answer. To get angle A, we're just going to subtract 75.52 and 57.91 from 180 to get 46.57 degrees. So our final answer for the solution of the triangle is given in this box here. We have our three sides, A, B, and C, were given as 6, 7, and 8, and angles A, B, and C are given as shown. Again, notice the larger the side length, the larger the angle across from it. Here's an unusual side example. Suppose you're told that you have side lengths A equals 3, B equals 6, and C equals 10. Can we find the measure of angle C? Let's start by plugging in what we know into the law of cosines. So we have 10 squared equals 3 squared plus 6 squared minus 2 times 3 times 6 times the cosine of angle C. Expanding out our squared terms and moving the constants to the other side is going to give you 100 minus 9 minus 36 equals negative 36 times the sine of angle C. We'll divide out both sides by negative 36, and you're going to get a decimal equivalent of negative 1.52778. The inverse cosine of that value does not exist. What that means is that in this case, there is no such triangle that will fit this situation. Here's a picture of what that triangle is supposed to look like. We've got the three sides, we've got 3, 6, and 10, but that short side is too short to connect to the third side. Now you might be thinking to yourself, wait a minute, couldn't you just move this down and get it to work? And other than the fact that this drawing is to scale, the answer is going to be no. This demonstrates what we call an example of the triangle inequality theorem, which states the sum of any two sides of a triangle must be greater than the length of the third side. Think of it this way. We've all heard that the shortest distance between any 2 points is a straight line. So if the straight line distance between point A and point B in this triangle is 10, then the distance traveled by going from point A up to point C and then back down to point B has to be bigger than 10. But if you look at it, we only have 6 plus 3, which is 9. So therefore, that triangle as we have it here can't possibly exist. So now that you've seen all the law of cosines and law of sines problems and seen how they work, we need to think about how you might be able to look at a problem and just know how to solve it. First, we need to take what information we're given and see which law is going to apply best. If you're given two sides and the angle not in between, or if you're given two angles and one side, doesn't matter if it's between or not, then you want to use the law of sines. Don't forget that if you have two sides and the angle not in between, you need to look out for the possibility of two solutions, one acute and one obtuse. If you're given two sides and the angle between, or if you're given all three sides, we want to use the law of cosines. If you're not given at least one length, you're not going to be able to solve the problem at all, and you should check to make sure you didn't misread something. Once you've decided what law you're going to use and you have to try to solve for the missing angle, always try working to find the smallest angle first. Why? Because the smallest angle in a triangle, which will always be across from the smallest side in a triangle, has to be acute. Finally, remember that although the law of sines and the law of cosines will work with any triangle, including right triangles, the rules of SOHCAHTOA that we looked at in section 6.2 will only work with right triangles. Granted, if what we have is a right triangle, it might be easier to use SOHCAHTOA, but I cannot apply SOHCAHTOA if I do not have a right angle in there to begin with. Let's look at some examples of trigonometry to navigation and orienteering. Compass bearings. When you're flying a plane or piloting a boat, based on the following, you see that you have 0 degrees is measured traveling north, 90 degrees is a bearing of the direction east, 180 degrees is due south, and 270 degrees is due west. Once you go around the circle a full time to get to 360 degrees, it starts over again. For land bearings, they typically don't use the 0 to 360 scale, but rather the bearing will specify how many degrees one is east or west of a north-south line. So for example, if you were to see the expression N 30 degrees E, that will translate into 30 degrees east of north, which is marked by this green segment here. Similarly, if you had S 65 degrees W, that's going to be read as 65 degrees west of south, which is this bearing over here. And that's essentially measuring 65 degrees from this north-south line over towards this bearing in the west. Here's some examples similar to what you might see on the homework. A pilot leaves an airport at 10 a.m. flying due south, averaging 300 miles an hour. At 1 p.m., the pilot changes her heading to 200 degrees, which is going 20 degrees west of south. Assuming she continues to fly at the same average speed, find the plane's bearing and distance from its starting point to its position at 3 p.m. Whenever I see a problem like this, the first thing I always try to do is draw a picture. Since I'm a horrible artist, I'm just going to go and try to find someone else's drawing and insert it into my own slideshow to illustrate the example better than I could ever hope to. So here's our situation. We have an airplane which is heading south for 3 hours, then makes a 20-degree turn towards the west and flies for an additional 2 hours. We want to know where we are with respect to the airport after 5 total hours of flying. Once we've drawn this out, we can label the three sides as A, B, and C. The angle that we're looking towards is going to end up, as we've marked here, angle theta. We could also call it angle B, depending upon how I've labeled the sides as A, B, and C in this diagram. So we're told that for segment A, we're traveling due south for 300 miles an hour for 3 hours, which means that we've traveled a total distance of 900 miles. Similarly, we're assuming that we're still flying the same speed for 2 additional hours after making the 20-degree turn, which gives us side B having a length of 600 miles. Knowing we've made a 20-degree turn, the obtuse angle that forms sides A and B in that triangle will have a measure of 160 degrees, because the big angle plus the 20-degree angle must add up to 180 because that's north to south. Let's set up the law of cosines here. So I have c squared equals a squared plus b squared minus 2 times a times b times the cosine of angle C. We can substitute our values into the general equation. A equals 900, b equals 600, angle C is 160 degrees, and we can type it into the calculator exactly as we see it to get a simplified value of 2,184,868.03 for c squared. Taking the square root of that will reduce to 1,478.13 miles. Now that we have the length of side C, we know that side C is across from the 160-degree angle. We can use the law of sines to measure angle theta, which will give us the number of degrees between side A, the south line bearing, and side C, our dash line. We can set the cross products equal to each other and then divide things out to get the sine of angle theta is 0.13883. So since we know this has to be an acute angle because this triangle already has an obtuse angle in it, we can get angle theta is 7.98 degrees. To answer the final question, we can say that the bearing of the plane from the airport is 8 degrees west of south, or a bearing of 188 degrees when compared to our compass rose above. Let's try one more example. Two planes leave an airport at the same time. The heading of the first plane is 350 degrees, which is 10 degrees west of north. The heading of the second plane is 49 degrees, which is 49 degrees east of north. If the planes travel at a rate of 420 and 510 miles per hour respectively, how far apart are the planes after 3 hours? Again, this might make more sense if we have a diagram to work with. So here's my airport and my two planes flying away from the airport in different directions. One is east of north, one is heading west of north. Here are the labels of the sides and the angles that we need to work with to make this problem make more sense. I've also added in a dash line to indicate which way is north because both of these bearings are represented as angles in degrees, so many degrees east of north and so many degrees west of north. The first plane is traveling at a rate of 420 miles per hour for 3 hours, which is a distance of 1,260 miles along a bearing of 350 degrees or 10 degrees west of north. Similarly, the second plane is traveling 510 miles per hour for 3 hours, which means it has traveled a total of 1,510 miles on a bearing of 49 degrees east of north. The angle between the two planes, based on our diagram, will be 59 degrees. We're looking to find out how far apart the planes are after 3 hours. So we're going to try to find the length of the segment marked as side C. We'll pull out our law of cosines and plug in what we know. We've got some pretty big numbers here, but again, with our graphing calculators, we can enter that expression on the right-hand side of the equal sign exactly as it's shown on the screen, and that will get you directly to the value of c squared being 1,942,719.2. To get the actual distance, we then just take the square root of that result, and that 1,393.8 miles will be the distance between the two planes. Now, if we wanted to find the other angles in the triangle to figure out what direction the first plane would have to go to chase down the second plane, we could use the law of sines now, but we're not asked to, so I wouldn't worry about it. Now, some of you might also be wondering about whether the curvature of the Earth is going to cause some problems with the measurements like we're doing with these airplanes here, especially with such long distances involved. The short answer is yes. These problems do assume that the Earth is flat, and so on some levels there is a lack of realism in these problems. When you're ready to take on a job as an air traffic controller, you will be able to explore these issues much more intimately in a way that goes well beyond the scope of this course. But for all intents and purposes, for problems like these, we're going to assume that the Earth is flat. All right, we've made it to the end of another lesson, and in fact, this one was a double lesson as we covered both sections 6.5 and 6.6. What you're probably thinking to yourself is that these video lectures are starting to get longer and longer, and you're wondering if that's going to be the trend for the rest of the semester. What I can say is that I'm trying to be well rounded in these lectures to provide a variety of examples while also anticipating a number of side questions so we can focus on what you absolutely want to see done during our ORT sessions. Will these longer videos continue to be a trend? Maybe for a little while until we're starting to feel more comfortable about the trigonometry subject material. And then we'll see. I'm also open to feedback on how these videos work for you. You can always include some commentary as part of a journal prompt, or you can put something on the discussion board. Anyway, here's the problem challenge problems for you to try from section 6.5 and 6.6. If you have any questions, you know what to do. Thanks for watching, and we'll see you all soon.